All right, good afternoon, everyone, and welcome to the Simulation Revolution demonstration. We're at the 2018 Altair Technology Conference here in Paris, and I'm very excited to present to you today our latest acquisition to the Altair suite of products, and that is Altair SIMSOLID. Now, before I go into details of Altair SIMSOLID, I want to quickly talk about the typical CAE process. And I'm sure many of you have seen this process through various presentations. At the same time, I'm sure you'll agree with the fact that most of the time that's spent in the CAE-driven process is spent in the pre-processing aspect. And there's two main elements of pre-processing where we spend most of our time. The first one is in preparing the geometry for meshing. And then once we have the geometry prepared, the next step is to actually go ahead and put the mesh on it. So if you look at this typical process and we contrast it with the process that it would look like when we use SIMSOLID, here's what that process would look like. So you can see now there's a significant reduction in the pre-processing time to almost minimal, to nothing, right? In addition to that, it's not just the pre-processing time, but you'll also see the time spent in the solver part of it is also greatly reduced. So overall, this is a much quicker and faster process. And in addition to that, it gives us the opportunity to run much more analysis, right? So let's say you were running 5 analysis to come up with a final design. But now with SIMSOLID, that 5 could be 50 designs that you would evaluate before you actually came up with a design process. So if you think of using this particular approach early on in the design process, the impact would be significant, not just to the design process, but to the design itself. So let's see how SIMSOLID goes about doing that. So first of all, SIMSOLID is a new paradigm for simulation-driven design. And how is it new? What is the new paradigm? So if you look at traditional FEA, it requires us to adapt the geometry so that we can put a good quality mesh on it. With SIMSOLID, it works directly on geometry. So what that means is we don't actually need to put a mesh on it. So SIMSOLID does not require a mesh to run an analysis. And the second important aspect is that SIMSOLID accepts geometry as is. So if you look at the top right-hand side of your screen, you'll see some typical geometry issues that we get when we import any CAD file into our pre-processing environment. You'll see thin sliver surfaces over here. You might have intersections, you'll have overlaps and penetrations. All that is accepted by SIMSOLID as is. And so if you look at these 2 points, you don't require to create any geometry cleanup, or you don't run any geometry cleanup operations, and you don't require to put a mesh on the model, and that saves a significant amount of time in the overall process. SIMSOLID is high capacity, and what that means is it is tuned to handle large assemblies and complex parts. So it's not uncommon to see assemblies that have hundreds or even thousands of components where SIMSOLID has been successfully applied to solve those kinds of models. And finally, when we run SIMSOLID, it's blazing fast and accurate. So what we've done is we haven't compromised on the accuracy to give you the speed, but we've ensured that you still maintain the accuracy while getting that high speed. So let's take a look at a few demos, and what I want to try and do is go through 3 quick demonstrations and show you how SIMSOLID can be applied to solve some real-world applications. And the 3 demonstrations that I'll go through will cover a modal analysis, will be a linear static analysis, and I'll even talk about a nonlinear static analysis. So here's a look at a typical crankshaft model, and you can see we've imported this into the SIMSOLID interface. There are various different CAD formats that are supported by SIMSOLID, and you can see here we support STL files, CATIA files, Parasolid files, files from ProE, SolidWorks, UG, and so on. So it supports all the commonly available formats that you can read in geometry into SIMSOLID. All right, and so now I have this crankshaft, and if I wanted to go ahead and run a modal analysis on this, I just select the icon that allows me to define my modal subcase, and over here it asks me how many modes I want to find. So for the sake of the demonstration, I'm going to select 3 modes. Now these are 3 deformable modes. It's a free modal run, so the 6 rigid body modes will automatically be calculated. So I hit OK, and the model is pretty much ready to run right now. So I go ahead and hit the run button, and SIMSOLID is going through the process, and you can see down at the bottom of the screen, it shows me the various passes that it's going through. And actually, before I could even finish my sentence, SIMSOLID has completed the analysis. So that's how quick it is. So you would have noticed as it went through the analysis, it actually did 3 separate passes. And what that is as it runs each simulation, it identifies the errors, and then it does a local refinement to reduce the errors. And that's what you see with each of those passes. And you can control that value to improve the accuracy of your overall solution. So let's take a look at these results right now. I'm going to animate the mode shapes, and you can see over here, we look at these results, and we have the first bending mode of the crankshaft. I can simply cycle through this, and there's my second bending mode. And then finally, I have my third mode, which is a twisting mode. So it was that simple to set up a model and run a modal analysis. I'm sure if I had to use the traditional FEA-based process, I'd probably still be in the process of finalizing the mesh, and let alone having a result in such a short span of time. All right, so that's the first example. The next example I want to show you highlights how we can do design variation studies. And what I mean by that is we're looking at model A versus model B type of comparisons. So here we have a grapple example, and we're going to compare how the performance of this grapple compares with another grapple design. For this case, I'm going to run a linear static analysis, and so this is where I would define that I want to run a linear static analysis. I can go ahead and specify my constraints, and what I'm going to do is click the surface on the inside here and choose to constrain that particular surface. And I'm going to apply a force on this lower surface at the bottom of the grapple assembly. So just define a force value. I hit OK, and I have my load condition that's been defined. So this model is now ready to run. All I need to do is go ahead and hit the run button, and you'll see it's popped up a message. It's basically telling me that I haven't assigned any material to the parts. Would I like to use the default material? And I think this is a very useful feature. What it does is you have an option here on the top, if you look at the project tree, where I can specify a default material. So that's useful. If you have a material that you use very commonly, you don't have to specify that for every single model that you use. Well, what you can do is simply leave it undefined, and then when you hit the job to submit a run, you get this message that pops up, and all you got to say is yes, which basically means it's going to apply the default material to all the undefined materials. And now it's off, and it's running the simulation. You can see it's doing the multiple passes. So by default, we do 3 passes. And you can see right now it's post-processing the results, and we're pretty much done. And this is a fairly decent assembly. It's got multiple components. It's got bolted connections. It's got pin joints. And it solved that in a very short amount of time. OK, so let's look at the results that we got. So here's a look at the displacement plot. And I can also do one thing. If I wanted to use these displacement results or any of these post-processing results to generate a report, all I do is hit this icon that allows me to save this as a bookmark. And then I can choose to export that data or export these images or animations and then use them in a post-processing type of result. So here's a look at the displacements. Now, the next type of result that I want to look at is my stresses. So I go ahead here, I choose the stresses. I can choose to animate them, so you can see over the course of the animation how the stresses vary. And then I want to save this animation so that I can use it later in my reports. Okay. So now that we've run the first simulation on this particular model, I want to bring in my second model, which is the variant B. So all I do is I go ahead here, and I can choose the location for my model, and I bring in variant 2. And what it does now, it's when I bring in a second model in the same project that I'm running, as it brings in the model, it identifies all the connections that exist in the components. So wherever you see the pin joints, wherever you see the bolts, it identifies those connections and automatically defines those connections. In addition, the other really useful thing that it does is all the loads and boundary conditions are automatically mapped. So if you look down here, this shows me the design study 2, which is the second model that I've brought in. But you also see here, I have the loads and boundary conditions that are already defined. You can see those are where I have my constraints. And then down here at the bottom, you can see I have my forces that have been applied. So I think that's a very useful feature, because as I'm doing these design variant studies, I don't have to sit and define my loads and boundary conditions every time I bring in a new model. That data is automatically mapped to the new geometry. So very useful to have that functionality. So now once I brought this model in, the loads and boundary conditions are automatically mapped. This model is ready to run. So I just go ahead and hit the run button. That's the same message that you saw on material. And you can see here, in a matter of seconds, literally, it'll be complete with the analysis, and the results will be ready for post-processing. And there we are, the results are ready, so I can go ahead and look at my results again. You can see here, these are the results for the post-processing on the second model, right? That's my displacement results, and then again over here I can look at my stress results. So the other useful thing that comes from these bookmarks is that if I click on the bookmark, it'll show me the results that the bookmark was saved for. But very easily, I can just simply click on the result from the model 2, and you can see that it updates not just the results, but it updates even the geometry along with the results on the second model. So it becomes very useful if you want to do a quick study between model A versus model B to have this option. Similarly, here I'm looking at the stresses, and you can see the stresses are being animated on the first model. But all I do is I simply hit result from my design study 2, and you can see it's updated the geometry as well as the stress contour to show me what the results look like on the second part. So that's, again, a very useful feature to compare multiple models. All right, so the other thing that I want to show on this particular model is, let's say I've done this study, and I now want to add an additional subcase. So there is one particular subcase that maybe I forgot to include in my initial study, or through certain feedback from the field, I find that it's important to capture that subcase. I want to include that now. So I can go back, and I'm going to include it to my first design study. I can just go ahead and create another subcase. So I say structural linear type of analysis. And again, I'm just going to simply pick the same surface that I defined previously. So that defines my constraints. So I hit my constraints over here. And now the forces that I'm going to apply will be on the other side of on the grapple arm. And again, I can go ahead over here and specify a value of -1,000 newtons and click OK, and the model is now set up. So I can go ahead now, and for my second subcase, I go ahead and hit run, and you can see now again, just like we did in the previous cases, we now have this new load case that's been applied, and our results are available. But the feature that I want to highlight to you over here is, now that we've applied this new load case, I want to be able to propagate that load case to all the different design variants that are in my project. I can very easily do that. All I have to do is go to the desired load case, simply right-click, and I say copy to all other design studies. And you'll see now if I come down over here, I have structural 2, which is simply copied over from the previous model, including all the loads and boundary conditions. And again, now all I have to do is simply hit the run button, and you can see how very easily, if I wanted to append a load case and simply copy it across all the models in my design study, I can do that very quickly and easily. All right, so let me bring up a third model that I want to show you, and this model is going to highlight how we can run a nonlinear static analysis. And so I already have this predefined in the interest of time. And you can see there's two subcases that's been defined. The first one is a linear static analysis, and the second one is a nonlinear static analysis. And the nonlinearity that we've included is contact. So it's very easy to check that. So you can see we have a settings option over here. So if I simply double-click on it, you can see this is where I can specify whether I want to include nonlinear contact, if I want to include nonlinear material, or if I want to include nonlinear geometry. So this is the first subcase. It's a linear static analysis, so I can leave all of those unchecked. For the second one, if I double-click on my settings, you can see that I've highlighted separating contact. So if I want to simulate separating contact, then I need to define the contact that's going to separate with the appropriate option. So when we bring in the model, it automatically defines these contact conditions, and you can see the configuration that's been defined automatically. So we have these conditions that are defined as bonded contact. You have some of them which are defined as sliding contact. But the ones that I want to define, which are these two contacts right here, are defined as bonded contacts. And what I want to do is change them to sliding contact so I can simulate the nonlinear contact behavior. All I need to do again here is simply double-click and then choose the separating option with a particular coefficient of friction value. So I do that for my first contact, and you can see it changes the representation from red to green, indicating that it's now changed from a bonded contact to a separating contact with friction. I can do the same thing for the other one. I simply go ahead, click separating, and I hit OK. And that's pretty much what I need to do to define nonlinear contact in that region. In addition to this step, what I also want to do is define some kind of a pretension to the bolts. So here we have a bolt and nut configuration, and we have multiple options that allow us to define how the nut can be tightened. So the way you would do that is simply go in there and pick the nuts. So all I'm doing right now is simply picking the geometry for the nuts on which I want to apply that particular, the nut tightening load. And there's different ways that you can pick it. You can use the control button and draw a box around it and pick those particular entities. So you can see here, I can specify a certain thread pitch. So I'm going to define a thread pitch. And there's multiple ways. So you can define the nut tightening through a number of turns, or you can define torque, or even a target axial force. So right now I'm going to specify a torque and define a particular torque value, and also choose to define friction. So I want to include friction in the calculation of the simulation while the nut tightening is occurring. So once I define that, I say OK, and you can see these arrows that essentially define that my nut tightening load has been applied. So with that, the model is now ready to set up. And again, like with the other cases, I simply hit the run button. And you can see again from the bottom of the screen the progress of the simulation. Now, in this particular case, we ran it with 4 passes. The idea is you want a little more accuracy. And that's where you may choose to increase the number of passes to accommodate higher accuracy. So the model is run. I actually wanted to show you the part where it analyzed for contact. But again, it was so quick that we missed that particular section. But again, you can see now that the analysis is complete. It's run the contact simulation. And I have my displacements that I can look at. I can look at my stresses. And I can even choose to animate the designs. And if I zoom in here, you can see that it shows me a very nice representation of the tightening effect of those nuts. Okay. And again, if I want to use the bookmarks that we saved previously, I can go ahead and choose a particular bookmark. This shows me the stresses in the bottom channels under the bonded condition, which is how I saved those bookmarks. And you can see the higher stresses are in the channels because it was bonded, so that's where you would see the maximum stresses. But if I simply click the results from my structural 2 situation, you can see that now the stresses shift to the bolt. And that's something that we would expect, because now that we've defined a separating contact, the cross channels can actually separate from the lower channels, and that would put a lot of bending stress in the bolts. So you can see from these demos that it's actually very simple and very easy to run these types of analysis. And we've run through very quickly through a modal analysis, through multiple linear static analysis, and even a nonlinear static analysis. And it's very easy and very quickly to do that. So just to quickly wrap up here. So we've seen that SIMSOLID is brand new technology. It's new technology that works directly on the geometry, and it does not require a mesh to be generated. It's extremely fast, as you've seen through the multiple demonstrations. It's very easy to use, and we do not compromise on the accuracy. So you get the accuracy along with the speed as well. And like I said in the beginning, it urges us to think of simulation-driven design through different eyes, right? And finally, just to conclude, if you want more information on SIMSOLID, you can go to our website at www.altair.com/SIMSOLID. There's also an option for you to download a 60-day free evaluation. So we highly encourage you to go to the website and request for an evaluation and try out the tool. I'm sure you'll love it. And finally, we do have a webinar planned for the 7th of November. So stay tuned for the email or notices about those webinars if you would like to attend and learn more about SIMSOLID. So with that, I end the demonstration. I'd like to thank you for your attention.